All right, welcome. Today we're going to dive into a pretty wild idea, one that comes from the very foundations of computer science. And it challenges something so basic, so fundamental to programming, that you might think it's just completely impossible to do without it. I mean, really, think about that for a second. No variables, no x equals 5, no temporary placeholders, nothing to store values in. How would you even do something simple like 2 plus 2? It sounds totally impossible, right? But believe it or not, about a century ago, this was a serious proposal, a way to see if logic itself could be built from something even simpler than we ever imagined. So this idea came from a logician named Moses Schönfinkel. In a paper from the early 1920s, he laid out this incredibly ambitious goal: to rebuild all of mathematical logic from the ground up, using just a few super simple building blocks. And he had one very strict rule: absolutely no variables allowed. So here's how we're going to break this down. First, we'll explore this whole idea of a variable-free world. Then we'll meet the 5 key building blocks he came up with. After that, we're going to see if we can actually build something with them. And finally, we'll kind of step back and look at the big picture and what it all really means. So how in the world did he pull this off? Well, Schönfinkel created this amazing toolkit of special functions that he called combinators. And these are the fundamental operations that, when you combine them in the right way, can do literally anything a normal computer can do. And here they are. That's it. The entire toolkit. It's just 5 operators: S, K, I, C, and B. Now, later on, they were given these kind of whimsical burden names, which is fun, but don't let the cute nicknames fool you. This right here is a complete Turing-complete system for computation. Okay, so at a glance, I know what you're thinking. This looks like a bunch of abstract algebra, but try to think of each line as just a simple rule for shuffling things around. These equations aren't just abstract. They describe concrete actions, like duplicating an item, throwing one away, or completely changing their order. Let's meet them one by one. We're going to start with the 2 simplest tools in the box. These guys handle the absolute basics, making a constant value and, well, doing nothing at all. First up is K, also known as the kestrel. Its job is incredibly simple. It takes 2 things, let's just call them X and Y for now, and it always returns the first one, X. It just completely throws the second one away. That's why it's a constant function, because it always gives you that first thing back, no matter what. So let's see it in action. If we give K 2 arguments, A and B, the K immediately grabs the A. Now this Ka pair becomes a new function, and its only job in life is to find the next thing in line, which is B, and just get rid of it. The final result? We're just left with A. Simple as that. Next up, we've got I, the identity bird. Now this one is even simpler, if you can believe it, but it is absolutely essential. The identity function does exactly what it sounds like. Whatever you give it, it gives it right back to you, completely unchanged. So you apply I to A, you just get A back. Now, it might seem a little pointless, right? But having a tool that can reliably pass a value through a long chain of operations without changing it, well, that turns out to be a really crucial piece of this whole puzzle. Okay, so we can keep things and we can discard things. Now we get to the power players, S, C, and B. These are the combinators that let us do the really cool stuff, like rearrange, duplicate, and compose functions in some really powerful ways. Meet S, the starling. This is the powerhouse of the entire system. It takes 3 arguments. We'll call them X, Y, and Z. And what it does is a little wild, so stick with me. First, it applies X to Z. Then it applies Y to Z. And finally, it takes the result of that first pair and applies it to the result of the second. So it basically distributes that third item Z to both X and Y before mashing them together. I know that sounds abstract, so let's check out a famous example, SKK. If we apply this whole combo to an argument, let's say A, the S starts by handing out that A to both of the Ks. That gives us Ka applied to another Ka. Now what does Ka do? We just learned this. It creates a function that discards its next argument. So the first Ka looks at the second Ka, throws it away, and leaves us with just A. So get this. The combination SKK does the exact same thing as the identity combinator, I. We just built one of our tools out of 2 of the others. And finally, we've got C and B. You can think of these as the organizers of our little assembly line. C, the cardinal, is a simple swap. Give it 3 things and it just swaps the second and third ones. B, the bluebird, is all about composition. It lets you chain functions together. So if you have b, x, y, z, it first applies y to z, and then it applies x to whatever that result is. This is the key to building sequences of operations. All right, we have officially met the entire toolkit. Now for the fun part. Let's put them to work and see how these simple little blocks can snap together to create some more complex logic, almost like a real programming problem. So here's our challenge. Can we build a brand new function, we'll call it P, that takes three things, A, B, and C, and transforms them into this BAC? What that means is it has to apply A to C first, and then apply B to whatever that result is. And the only rule is we can only use our 5 fundamental combinators. Okay, the first thing you might notice here is that the pattern B of ACC looks an awful lot like function composition, right? You're applying one function to the result of another, and hey, that's exactly what B, the bluebird, is for. Remember its rule? B x y z equals x of y z. In our puzzle, x is B, y is A, and z is C. So we can rewrite our goal as B, B, A, C. We're so close. But to define P as its own thing, we need all the arguments A, B, and C to be at the end in the right order. Right now we have B, B, A, but we need A, B. So we need to swap the B and A that come after the B. And what's our tool for swapping? It's C, the cardinal. Applying C lets us reorder the expression so we can get our functions all grouped together at the front. And now that the C and the B are sitting right next to each other, we can just group them. See, in this system, function application always groups from the left, so we can treat C and B as a single, new function. This new combined CB function is what's going to be applied to A, B, and C. And there it is. That's our answer. Our new function, P, is simply CB. We just created a new, very specific operation just by snapping together two of our simple general-purpose blocks. This right here is the heart and soul of building logic without variables. This simple example, it really gets to the core of what Schönfinkel's strange-looking system reveals about logic and complexity itself. I mean, just let that sink in. From just 5 incredibly simple rules for shuffling symbols around, we can construct an entire universe of computation. You can represent numbers, you can represent logic, you can build any algorithm you can possibly imagine, all without ever once needing to name a single variable. It's just mind-blowing complexity, emerging from the simplest possible foundation. And that kind of leaves us with a final thought to chew on. From the laws of physics that build entire galaxies to the genetic code that drives all of biology, how many of the complex systems we see all around us are really, at their core, just the result of a few simple rules playing out over and over again on a massive scale? Thanks for exploring this with me.